kinematics. So kinematics may seem like a scary word, but the simple thing, it's quite straightforward. The study of kinematics is the study of the motion of objects without considering what causes that movement. So there are two parts. There's kinematics and there's dynamics. Dynamics is interested in the forces that are involved on the system, whereas kinematics is only interested in the motion. So, how fast is something going, how far is it gone, what's the acceleration, things like that. So, for example, by observing dropped objects, I can figure out that objects on the Earth accelerate downwards at 9.8 meters per second squared without knowing that it is caused by gravity. So in this first module, you'll be looking at motion in one dimension, which is just along a straight line, and in two dimensions, which is on a plane. So the warning here is that this isn't a theory-heavy module. It's to introduce the methods and the theory to... so the goal here is to introduce the methods and the theory required for you to go home and put the work in yourself. So yeah, again, with these sort of kinematics questions, it comes a lot with, actually doing questions and becoming comfortable with more and more complex setups. And when we talk about kinematics, kinematics is definitely used a lot again in year 12. So it's a big part of, so it's like commonly used in year 12 in order to apply, or I guess you would use the content from year 12 in order to solve problems. And then let's just say you get that the acceleration is a certain number, then you use that alongside these kinematics formulas in order to figure out what the final velocity is or something like that. So it's used alongside the year 12 content. So to appropriately describe motion, we need to know about vectors. Now there are two types of quantities in physics. There are scalars, which have only magnitude, and there's vectors which have both direction and magnitude. And vectors are very important in kinematics because a lot of quantities which you deal with in kinematics are vectors related. So you've got velocity, acceleration, displacement, they're all vectors. But first, let's talk about what a vector is. And one of the ways that vectors are represented is just as an arrow. So what I mean by that is, if we have a vector, right, that starts at point A and finishes at point B, then you've got the vector AB, and it's denoted by a little arrow like this, or sometimes you might see a lowercase a with a little tilde underneath it, or a little squiggle underneath it called a tilde. So yeah, a tilde, that's called a vector. Now the key thing with vectors is they've got a magnitude, which is how big it is, and the direction. So for example, when we're talking about velocity, right, if you've got 6 meters per sec, if we're talking about speed, which is a scalar, right, speed is a scalar, and so it's going to be saying something like 6 meters per second. Whereas vectors have both the direction and the magnitude. So the magnitude might still be 6 meters per second, but the direction might be something like north or east. So velocity would be saying something like 6 meters per second north, whereas the scalar version, which is speed, would be 6 meters per second. Now, we can represent vectors in many ways. A good visual method is an arrow, so like I said here. So the arrow has a length, which corresponds to the magnitude, and the arrow has a direction, corresponding to the direction. So if we have vectors, right, the longer the vector, the greater the magnitude. So sometimes people use a scale to draw them. Now, it's not always drawn to scale, but you can use a scale to draw them. So maybe 30 meters might correspond to 5 centimeters something, and so 60 meters is going to correspond to 10 centimeters, so you're going to draw your arrows like that. But yeah, it's got a magnitude and a direction, and so this allows us to visualize things like adding vectors, subtracting vectors, and so on. So when you have two vectors, vector A here and vector B here, and you want to add those two together, you're going to put the first vector down, and then you're going to take the second vector and put it tip to tail. That's the key words here, tip to tail. So you put the tip of A to the tail of B, and then you close off the triangle by putting in this vector here, right? Maybe I'll rub that out so make it clear. So you put in this vector here, and that closes the triangle, and there you have it. That is the resultant vector, or that's what you get when you add those two vectors together. So remember, you start at the tail of the first one, and you end at the tip of the second one. Well, once you put it up tip to tail. So when we discuss kinematics, we take things like subtraction and scaling vectors is something that we'll look at in a bit more detail soon. But vectors, just as a side note, is a specific topic in itself in Mathematics Extension 1, if you guys are going to do that in Year 12. But vectors, like, it's a very general concept, because vectors you can deal with 3 dimensions, 4 dimensions, 5 dimensions, infinitely many dimensions if you wanted to. But the key thing here is to note that like many of the quantities that are dealt with in physics are vectors, and that's why we use this concept from maths called vectors in order to describe many of these concepts. Okay, so this is a little practice here. So first we want to identify which of these are vector properties and which ones are scalars. It's okay if you guys have never heard of them before, just guess if you would like to. So yeah, maybe I'll give like 10 seconds for you guys to have a think about that. Try and classify each one of these as either a vector or a scalar. Yeah, that should be good. Okay, so time. Now this one's sometimes debated because people are interested in whether you can go backwards in time, but well, yeah, it's a bit debated in that sense. But I think for our purposes, at least for kinematics, we can quite safely say it's a scalar, because it's not something that we have direction. You would say 3 seconds or 10 minutes or 1 hour, rather than saying 1 hour north, or like yeah, it's not really got a direction, I don't think. You could say backwards, but I don't think that's very relevant in this case. When it comes to acceleration, that's definitely a vector. We'll talk a bit more about what acceleration is, but you would have seen this concept before. Definitely, when you step on the accelerator, you accelerate your car. What does that mean? It means you speed up. So acceleration is a measure of how fast you speed up, but it's a vector because it also has a direction. So maybe you go 3 meters per second squared, 3 meters per second squared north, or maybe when you drop an object, it goes 9.8 meters per second squared downwards. Now, we've got distance and displacement here. On the surface, it looks like they're two very similar quantities, or like they're equivalent quantities, but in reality, they're different because of this scalar vector thing. Distance is a scalar, right? So if you say 2 points are 10 meters apart, that's a distance, whereas displacement is a vector, because you could say something like, if you have a coordinate plane, you're going from here to here, 30 meters northeast, for example, right? So that is a vector. Displacement would be something like 30 meters northeast or 30 meters to the right, whereas distance is just a scalar. You've got 30 meters. There's a bit more of a strict definition to displacement if you talk about how far it is from your original position. So an example which quite often gets talked about is if you're doing laps around a field, for example, right? Let's say the total distance around a field is 400 meters. Let's just say you do 1 lap and you come back to the point that you started from. So your displacement at that point would be 0 meters, whereas your distance that you've covered is 400 meters. And if you do another lap, your displacement is still 0 meters, whereas your distance is 800 meters. So there is a subtle difference between them. Speed is pretty much what we talked about before. It's like saying 10 meters per second or 5 meters per second or 30 kilometers per hour. It doesn't have a direction, so it's a scalar. Force, however, does have a direction, because not only does it have a magnitude, it also has a direction which the force is applied. So you could say 10 newtons downwards, or 30 newtons to the right, or 30 newtons forwards or something. So that's a vector. And velocity is a vector. So it's like you could think of it as speed with a direction, or you could think of speed as a velocity without direction. Technically, there is a bit more of a subtle difference between them, but I think it's okay to say that velocity is a vector, speed is a scale. Okay, so when we discuss kinematics, we typically care about 3 things: where an object is, so position; how fast it's moving, right, that's velocity; and how fast this movement is changing, and that's acceleration. So, yeah, maybe I will briefly introduce the notation for this. So displacement is sometimes given as just s, right? And the velocity of an object is quite often v, or sometimes it's given u, depending on, yeah, we'll come to that in a second, but just remember it's either v or u. Acceleration, which is how fast the movement is changing, is given by a. So the scalar version of this, the scalar version is distance, and the vector version is displacement, like we said before. So 30 meters or 30 meters south. Speed would be 10 meters per second, and then velocity would be something like 10 meters per second downwards. Or acceleration doesn't really have a scalar version, so vector version would be something like 20 or 10 meters per second squared east. So basically, displacement is where we are relative to some origin, and with the word origin is put in quotations here because technically we can choose where our origin is as long as it's what's called in now, like the regular law. If we're going to stick with our regular sort of formulas and things, as long as a inertial frame of reference, then we can pick whatever frame of reference we want, and we can pick what the origin is. There's velocity, which is how fast we're going. How fast our displacement is changing. So you see either v equals d over t, or you can see v equals s over t, or sometimes even change in position over change in time, because if we have a starting point somewhere here, and we have a start ending point somewhere here, we have s initial, s final, right? And so we have not just a displacement, we have a change in position. So, well, that is a displacement, but we have s final minus s initial. So we have a displacement. If you use this sort of formula, it's sort of confusing as to whether you're going to sub in sf over t, or whether you're going to actually sub in the displacement. So acceleration is how our velocity is changing, where our velocity is going. So acceleration is the rate of change in the velocity. So we have acceleration equals to the change in velocity over change in time. So for example, if someone speeds up, here's a quick example. Maybe I'll open up OneNote to give us a bit more space. So acceleration example would be if someone speeds up from, let's say, 60 kilometers per hour. Sorry, let's say someone speeds up from 60 kilometers per hour to 100 kilometers per hour. So we have change in velocity of a change in time. So we have v final minus v initial. That's a change in velocity over the change in time, or however long it takes to do that. So the final velocity, let's just say, is 60 kilometers. Final velocity, let's say, is 100 kilometers per hour. So that's how fast the person gets up to. And then the initial velocity was 60 kilometers per hour. That's how fast the person was initially traveling at in that car. And then TF minus TI is how long it takes. So let's say it takes 10 seconds. No, I think it's probably closer to maybe let's say 7 seconds, right? To get the units right, we're going to have to convert from seconds to minutes. Seconds to hours. So we're going to have 7 divided by 60 to give it in minutes, divided by 60 again to get it in hours. So 1.944 times 10 to the minus 3 hours. Yeah, so 7 seconds. And if we put that into the calculator, so 100 minus 60 is 40, divided by 1.944 times 10 to the minus 3 is 20576.13 kilometers per hour squared. Now, those are a bit of funny units. We'll be dealing with meters per second squared a bit more often, but if we're dealing in kilometers per hour squared, that's the answer. So if we look at another example, acceleration of, let's say, gravity, for example, 9.8 meters per second squared. What does that mean? That means initially, so let's say the object is initially at rest, the velocity initially would be 0, so VI would be 0, and let's say after 1 second, what would it be? That would be 9.8 meters per second. After 2 seconds, it'd be 2 times 9.8, or 19.6 meters per second. And after 3 seconds, it would be, if I put that in the calculator quickly, make sure we don't make any mistakes, it's 29.4 meters per second, and so on. So acceleration means that that a object or a car or a person, whatnot, is speeding up, right? And so it means 9.8 meters per second each second. So it's speeding up by 9.8 meters per second each second. That's what acceleration means. And we'll come to some more specific formulas to deal with each one in a second.